So we're focusing today on n-gram language models. First of all, let me give you a definition of an n-gram. It's just a sequence of n words that occurs consecutively together. Sometimes informally it'll be things that occur quite often together, but technically it's really just any consecutive sequence of words that occurs. So for example, unigrams, 1-grams are simply individual words that occur. So arsenal, 2, listed version of the tower. All of these are random individual words that I selected out of a corpus, a Wikipedia data set actually. Bigrams are consecutive word pairs. Into a and placed, the mint, businesses and. All of these are naturalistic bigrams. Trigrams are 3, for example, as an addition, their significance and. 4-grams, developed in illness characterized, evening class at the. These are all naturalistic examples. And of course we can make n-grams, the n can be as large a number as you want. Now, these turn out to be relevant for all sorts of things, for human language production, spoken dialogue systems, machine translation, more. And going back to these examples in speech recognition, we can look at, for example, let's take the tail example in the context of after dogs. So if I look in naturalistic use, frequency use, it turns out that there's an enormous bias conditioned on seeing one of these two bigrams on it being the TAIL bigram, not the TALE bigram. It's a 6,000 to 1 ratio. If I switch it around, tail of a dog, it's still biased, it turns out, to the TAIL interpretation, but it's much less strong. It's actually 750 to 1. You can see that there's information here that's contained in these co-occurrence statistics, and this gives rise, this is actually the basis, or you can even think of as a formal characterization of a conceptual intuitive notion that's played a role for a long time in language teaching, in corpus study of language, and that's the notion of collocationality. A collocation is a word sequence that occurs, quote unquote, unusually often. So I want to probe your intuitions and just give you a little bit of experience judging these. I'm going to give you a set of word pairs that either have nearly identical meanings or at least are reasonably comparable in terms of they might occur in similar contexts. And I want you to judge which one of them sort of sounds more like it's a collocation, sounds more like the words go together. And I think you're going to find that the intuitions are very natural about this. So here's the first example. Young childhood or early childhood? I think probably most of you feel that early childhood is a more natural way to say it, even though you might think that those are actually probably going to mean the same thing. Second example, mass destruction or illegal destruction. These probably don't mean exactly the same thing, but even so, I think you can judge that mass destruction is somehow, those two words just go together in a way that illegal destruction, it just doesn't go together. Good cuisine, ethnic cuisine. Once again, I think you're going to have a strong intuition that both of these are perfectly reasonable things to say. They don't mean the same thing. Nevertheless, you can judge that of the two, ethnic cuisine is sort of more of a thing. And this notion of collocationality is very interesting from a cognitive perspective, because there's nothing wrong with any of these 6 bigrams. They're all perfectly reasonable bigrams of English. But it seems that for each of the cases, relative to its comparison bigram, we have a bigram that somehow sort of seems more like it lives in English. It maybe sort of has its own existence, or it feels like it's sort of more entrenched or more strongly represented in the mind, more natural to say. And what that actually means is a very interesting question in the study of cognitive science of language. And by the end of today, by the end of this lecture, we're going to get to try to formalize this a little bit more, and it turns out that we're actually going to be able to quantify this idea, or at least put forward a hypothesis about a quantitative representation of what it means to be collocational. Before we do that, I want to get to actually moving from n-grams as a thing to a probabilistic model built on n-grams. So we'll start off by saying, okay, we have a word string, we'll call that W with a vector over it, and in the general case, that's going to be a beginning of sentence marker, which is that bracket S, and then a sequence of n words, and then end with a special end of sentence marker. That's going to be our word sequence. And we are fundamentally interested, as I said, in putting probability distributions over those things. What's the probability, for example, that the next sentence is going to be the sentence dog chased cats, which will be represented as you see here. The first thing to do, and this is not specific to n-gram models, but to many kinds of language models that you might want to look at and build and that are used today, is to remember the chain rule decomposition. The chain rule decomposition says that a collection of events, the joint probability of a collection of events, can be decomposed as the product of the conditional probability of each event given all the other events that have already been generated. So you define an order on the events, and then you conditionalize where it's the probability of the next event given all the previous events in whatever the order is. And a natural ordering in natural language is just the temporal or linear ordering from first to last. So if I apply this to our sentence, then we get the decomposition that the joint probability of the sentence being dogs chase cats here is, well, I have to start a sentence. This is obligatory. I have to start a sentence with the beginning of sentence marker. So that has probability 1. But all of the other probabilities are going to be the probability of dogs given the beginning of the sentence. So dogs being the first word of the sentence. Chase being the second word of the sentence given that the first word is dogs. Cats being the third word given dogs chase. And then that the sentence ends after the word cats, after the whole string dogs chase cats. So that's the joint probability decomposition using the chain rule. And I haven't made any assumptions at this point. I want to emphasize that. This is simply the application of the laws of probability. I've made no assumptions, no simplifying assumptions. There's no n-gram assumptions here at all. The n-gram assumption comes in by assuming some kinds of conditional independencies between a particular word and the preceding contexts. As a simple illustration of this, we'll focus on the bigram model. The general case is that for an n-gram model, only the last n-1 words matter. So a bigram model, which is n equals 2, says that the current word that we're generating is conditionally independent from all the words that are 2 words back or more, given the immediately preceding word, i-1. That gives us a bigram model. And crucially, that tells us that we could decompose this probability. We can further simplify this chain rule by eliminating all the words that are not the immediate preceding word. So I would get rid of this, I would get rid of this, and I would get rid of this. This is resorting to the definition of conditional independence. And I get what's on the bottom. I get that this joint probability can be decomposed as the product of the probability of dogs given the beginning of the sentence, chase given the dogs, cats given chase, end of sentence given cats. That is a bigram model that puts a probability on this sentence. And if we do this and then we can actually generate from this model, so these are great fun examples where you train models on Shakespeare of various n equals 1 through 4, and then you generate from them and you get things that are interesting. So for example, the unigram model generates things that have Shakespearean words but don't have any structure. Once you get to a bigram model, you get things that look sort of locally okay, but then really sort of wander off in weird ways. As you go to higher and higher order n-grams, you get things that are more and more coherent. But when they're long sentences, you'll see that they're really still not that globally coherent. For example, a great banquet served in is not a coherent sentence. You can do this to the Wall Street Journal, for example, and you get similar results. The content is and the style are obviously different. But once again, with low order n-grams, you don't have a lot of coherence. Okay, so that's an illustration conceptually of what kinds of probability, what kinds of things are okay in an n-gram model. And you can see that clearly these are not great models of language, but they're still of a lot of interest for a lot of reasons. Partially because for a long time they were very good, they were the best that we had, but also because they may capture interesting elements of human knowledge. And furthermore, for pedagogical reasons, they help us break into conceptually what a lot of the crucial issues are in estimating probabilistic models for language. So how do I estimate a model like this? Here's the general scenario for probability estimation, and I'm going to use it to introduce a very simple method that is a conceptually important starting point. The general scenario is that I want to estimate some conditional probabilities. I'll call them the general case. These are y given x. So random variable y given some other random variable or collection of random variables x. And I have some training data consisting of some xy pairs. So for example, if I'm estimating a bigram model, these would be previous current word pairs. And I've chosen a model class. And model class is a special thing in statistics and in machine learning. It is a parameterized family of probability distributions. And what that means is it's a set of probability distributions where the differences among the probability distributions can be connected with different choices of the parameters in the model. in everything that we're going to look at here, there's going to be a model class that we're looking at. So bigram model, for example, is a model class. Now, given the model class, we have to ask, okay, so how do we get to the estimates of the probabilities in that model class? And I'll start with what I think is useful to think of as a really basic, central, fundamental, but not usable in a lot of cases satisfactorily approach, but still important to understand. And that is the method of maximum likelihood estimation. This does not work well in practice for language models, but it is a conceptually important starting point. So I'm going to illustrate this first, and then we'll talk about what goes wrong with this for language models. And then we'll address ways of fixing the wrongness. In a lot of other cases, depending on the problem that you want, maximum likelihood estimation might be perfectly okay. And even if it's not, it's a useful thing, it's a useful sort of anchor to think about when you're thinking about what actual estimation technique to use. So let's go forward with this. So once again, we have this general scenario, which we illustrate in the upper left. And let's consider us estimating a bigram language model. So we want to estimate these bigram probabilities. I have some sentences. The bigram model family says that each word could be its context, could be the context that you care about. And the bigram assumption says that each of these words has its own multinomial distribution over next words. So the kind of model that I want to estimate is one that, for example, this might be our data set. From this, I would estimate some conditional word probabilities given a previous word. So, for example, if the preceding word is, quote-unquote word, is the beginning of the sentence, then I might want to get out a distribution like this, where the word the is very common, very likely, and verbs are very unlikely. If the preceding word is the word bark, then I might want to have a distribution that maybe it's likely for the sentence to end. Maybe nouns are a little more likely to than verbs, and so forth. And if the previous word was the word birds, then maybe I'm also likely to have the sentence ends, but I'm more likely to have verbs than nouns. So I sort of want to get something out, a data representation that looks like these histograms in the lower right. Think of those as one multinomial distribution per possible context. And I'm trying to estimate all of those multinomial distributions. That is the problem of bigram estimation. Okay. How do I do this? First of all, I take my raw data, my training data, my corpus, and I will now think about, just conceptually to understand what maximum likelihood estimation says, as follows. Let me consider each multinomial parameter, so each sort of histogram width, bar length in the previous slide, as that's a parameter in the model, and I'm going to consider each one individually. For example, I might be interested in the probability that if the previous word was dogs, the next word will be bark. That should be not one of the lowest probabilities in my model. Okay, so I will first summarize my data in terms of the raw, what are called sometimes the summary statistics of the data that are enough for me to estimate my model from. In the case of a bigram model, all I need to estimate the model is the bigram counts. And so this is a collection of the bigram counts in the case where the preceding word was dogs. I have 4 overall cases of that. 3 of them have the word chase next. 1 of them has the word bark next. Now, let's imagine I want to know what should I estimate for that probability of bark given dogs. So in order to figure that out, so here once again is the relevant part of my corpus for this. First of all, we can also note that there's another probability. Let's just sort of think of, we'll define an event, which is the event that dogs was in the context, and the next word is, given the dogs is in the context, the next word is not bark. Well, that's 1 minus p by definition because of properness of probability and disjoint union. So now we can define what the likelihood is. Remember, the likelihood is the probability of the observations given the model. And so the likelihood for this little chunk of the data, we would say is, well, there's 1 instance of bark, so the probability is p times 3 instances of not bark. So that's 1 minus p cubed. So for this sort of representation, I can think of the likelihood as having this form. This is an oversimplification because, of course, there are going to be many different parameters, one for each possible next word. But nevertheless, everything that I'm going to say here will hold and go through and generalize to that broader case. In this case, where I'm just thinking about one parameter, is conceptually very simple. Okay, so I have this situation. Now it turns out that with maximum likelihood estimation, I'm going to take the likelihood, which I've encountered before in the context of Bayesian inference, and I'm now going to think of the likelihood as a property that is a function of the parameter or parameters that I'm interested in estimating. In this case, the parameter I'm interested in estimating is this probability p that, given that the previous word was dogs, the next word will be bark. Okay, and I'm going to ask, suppose that this is the relevant part of my data because this is the part of my data where the previous word was dogs. On the x-axis here I have p, and on the y-axis here I have the likelihood of the data that's in the box on the upper hand, which, as I said before, is p times 1 minus p cubed. And that is this curve that I've shown here. Now, the method of maximum likelihood says that I want to set my parameters to the value that make the data as likely as possible. So I want to set my parameters to the point where this curve will be at its highest. That's this point that I've illustrated in green. And if I plot down, I find out that this probability, this value of p is 0.25. That's exactly where the maximum likelihood is found. Now, you'll notice something interesting. So the maximum likelihood estimation says I should set this parameter p to 0.25. Now, you'll notice something interesting about this value, which is it's also, so this is choosing the maximum likelihood estimate, this is also the proportion of times in the data that when the previous word was dogs, the next word was bark. So it's 1 out of 4. And that's exactly what the maximum likelihood estimate is. And that is not an accident. In the case of multinomial estimation, the maximum likelihood estimate also turns out to be what's known as the relative frequency estimate. And this is like the most intuitive thing, I think, when you get into trying to infer probabilities in these discrete cases. You just count up events and then you divide by the conditioning event count, and you have in the numerator the outcome event count. So this is literally the ratio of the count of dogs bark to the count of dogs in the context. And this actually, the point here is that this shows that there's a very deep principle behind that method of counting up and doing relative frequencies to estimate probabilities. This is the method of maximum likelihood. But the method of maximum likelihood is much more general because we can apply it to many, many other kinds of models that don't have a relative frequency approach that you could use. Okay. Now, it turns out that that's a really, really bad idea, and I want to show you why. For this case, while the method of maximum likelihood is important to understand, you don't want to use it in estimating language models. So for example, here's our training data for the entire thing, and this is a different representation. I've just listed the contexts, and for each context I list the events and their counts. So for example, in the context of the, cats occurs once and birds occurs once, and so forth. Now suppose that I learn using method of maximum likelihood this a model from these data, and then I have a new observation that I want to predict, which is I want to ask the probability of the new sentence being birds chirp. Well, I've never seen the word chirp in my training data followed by the end of a sentence. And so this sentence would get probability 0. And that's a huge problem. What it indicates is that maximum likelihood estimation gives no generalization to unseen events in the n-gram representation. So if I didn't see an n-gram in my training data, I assume that it's impossible. And that's a really bad idea because language is sparse. Most things that you'll encounter in the future you will not quite have encountered in exactly the same form in the past. So we have to do something different. And what I'm going to now present to you is a number of ideas in increasing complexity of how to solve that problem in the context of n-gram models. And you don't need to sort of memorize or deeply study all these ideas from a technical standpoint. I mainly want to introduce to you the conceptual intuitions because they're very valuable intuitions. N-gram models are no longer state-of-the-art. You're not going to see them used in contemporary applications, but there may be scientific applications and other settings where it's still useful to look at what n-gram models would do, and you want to keep in these ideas in mind in terms of how to actually deploy them in a reasonable way. So once again, let's go. This is our counts from our example. So in the context of the word dogs, here's our vocabulary. all the possible things, but most of the possible things in our vocabulary actually didn't occur in the training data set. Bark occurred once, chase occurred 3 times. The idea of additive smoothing is that we're going to take the actually observed count of each context event pair, and I'm going to add to it what's called a pseudo count. So in the simplest version of this, I add a pseudo count of 1. It's as if I had seen every bigram that is made possible by my vocabulary, as if I had seen every such bigram in the training data once. So I'm going to transform the original counts into the add 1 counts, and just by adding 1 to each of these counts. So whereas the original count of end of sentence in the context of dogs was 0, it's now 1 in the add 1 count. Bark after dogs is 2, and so forth. And now I'll just so now this leads to an equation. I'm going to use these add 1 counts for a sort of a pseudo relative frequency estimation. So I'll do what would be relative frequency estimation on the add 1 representation. That means that the resulting equation is that I estimate, and this is known as Laplace smoothing, after the great mathematician Laplace. I'm going to estimate the conditional probability of a word given its context as the joint count of the word and its context plus 1 divided by the count of the context plus the vocabulary size. And it's the vocabulary size because for a given context, it will get 1 count for every other element in the vocabulary. And so that means that the vocabulary size will be in the denominator. So, and I do this for all of the other context event pairs as well, and so forth. Okay, so this is one simple idea. So as an example, what does this do? So for example, in the context of the word bark, what happens to the probability of the sentence ending next? So in the maximum likelihood estimation, because bark was only seen once, and the sentence ended after it, the maximum likelihood estimate would put a probability of 1 on the end of a sentence in this context. But in the Laplace smoothing, it becomes this is wrong, it should be 1/7. Here, because I've added these 6 pseudo counts here. Okay, so this is a big change. You can see additive smoothing with add 1 has a huge effect. And it's actually even more massive than that, because if you think of the number of logically possible n-grams, it's the bigrams is vocabulary squared, trigrams is vocabulary cubed. The number of add 1 counts will vastly outnumber the actual observed data. And so additive smoothing like this is a very, very aggressive smoothing technique. And this is a big problem because it puts too much extra probability for these rare contexts. And once again, those are rare and those are typical in the sense that most of the logically possible combinations of context and words in an n-gram representation will never have occurred in the data, and a lot of them really are unlikely to have ever occurred. So for example, of in will never occur. So we can generalize this idea, for example, by adding less than 1 to each count. So I can change that 1 to this value lambda, and so lambda can vary to any number, and you can try to find an optimal value of lambda, and that's actually the basis of the p set that you have right now. This, once again, you can do this. This is still not super great in practice, and just to give you a set of intuitions about this sort of treats all context event pairs as equal in terms of the additional probability mass that you're trying, where you're moving the probability mass. You're sort of moving probability mass away from observed things and toward unobserved things, and all the unobserved things in the n-gram representation get equal mass. And the problem is here that this doesn't capture a couple of key insights. We should be really making different generalizations about different kinds of context and different kinds of events, and additive smoothing doesn't distinguish context event pairs at all. Just that all context event pairs get some additive smoothing. So that's really not a very sophisticated approach. So now what I'm going to run through is a few different ideas that have occurred in the n-gram literature and have been very influential. And once again, the technical details are not that important. It's the conceptual move. What is the intuition that's being capitalized on? And you will see these if you go back in the literature, and you may see them in new papers. Mainly, I want you to understand what they're trying to do. Okay, so the first of these additional ideas is what's called model interpolation. So suppose I have 2 different models, maybe a bigram and a unigram model. Okay, I could actually say the model I'm going to use is actually sort of an average. It's a weighted average of the 2. And so now I'll take, here in this slide, lambda is the relative weights of the bigram and the unigram model. So if I set lambda between 0 and 1, I have what's called an interpolated model. I've taken a linear combination, an interpolation, of these 2 models, the bigram and the unigram. And so as I dial lambda up, it's going to look more like a bigram model. As I dial it down, it's going to look more like a unigram model. And this modification of a standard bigram model is unlike additive smoothing in that it makes different generalizations about different events. It says that above and beyond the bigram context, what direct information I have about a particular bigram context, I'm going to predict a word to be more probable insofar as it's more probable overall in all contexts. That is captured by its unigram count. That's how it does it. More words that are more frequent overall become more expected regardless of context. Also, you can do other things, like you can make the interpolation weights a function of the context. So I could say that actually I'm going to change this interpolation weight to take in the context, say in a bigram context, the previous word, and I'm going to spit out a weight. So for example, a context that I've seen a lot might intuitively get a high lambda value, and a context that I haven't seen a lot should get a low lambda value because I don't have a lot of information about it. And we can extend this also to higher order n-grams. So that's idea one. Here's idea number two. The more rare events a context has, the more events we should expect it to occur in. Okay? So this is a context type diversity. And this is sort of related to the notion of good Turing smoothing. And the idea about good Turing smoothing here is, let's suppose that in my training data set, I have words that never occurred in a particular context. I have words that occur once in a particular context and words that occur more and more. And the idea is here, well, first of all, most words occur rarely in any given context. But really, seeing a word once is sort of very similar to having never seen it. In fact, before you saw it once, you had never seen it. Before you'd seen a word twice, you'd seen it exactly once. And it also turns out that if you look at held out data, then actually the number, empirically speaking, a lot of the times, the number of times you'll see an n-gram, you'll see a word in a particular context in a held out data set is a little bit less, but not a huge amount less than the number of times you've seen it in your training data set. And that's because, first of all, because of data sparsity, seeing anything at all, anything you have seen, you're probably overestimating its probability, but you're not overestimating its probability a huge amount. And the conceptual idea about good Turing smoothing is that you actually treat words, you treat possible events, you're going to try to treat them as events that have occurred a little bit more than they actually have. So you're going to use, for example, the overall count of singleton events for a given context as a basis for estimating the probability of events that have never occurred in that context. And you replace the overall count, the estimate of singleton events in the context with the information you have about doubleton events that have occurred twice. And there's some fancy math that you have to use to make this distribution more proper again. But that's the fundamental idea, is that you basically sort of push down probability mass for a given context from events to as if they were of a slightly different count. So that's the event diversity of a context. And then one more idea is the context diversity of an event. Okay, and so the intuition here is, let's take an example of here. So I can't see without my reading what comes next. So let's take the word glasses and the word Francisco. And imagine that neither of those had occurred in a particular context that you've seen. I've never seen glasses or Francisco in that example. But I wanted to predict which one would happen more often. So Francisco and glasses may not differ that much in frequency. And so you might not do well to differentiate them using, say, model interpolation. But one thing you know about the difference between glasses and Francisco is Francisco only ever occurs in a very small number of contexts. If it's not in the context San before it, it's not very likely to occur. Glasses can occur in many, many, many kinds of contexts. And so the idea there is that when you're predicting what might happen in a context, you should be more optimistic that something that occurs in a lot of different contexts happens, even if you haven't seen it yet in that context, than you should be for something that only occurs in a few contexts. And so the way of operationalizing this idea is by defining sort of a number of, basically counting up how many different contexts a word appears in. And that's what's called the continuation probability of the word. And we're going to, when this continuation probability is large, that word occurs in lots of different contexts. When it's small, it occurs in only a few contexts. And then you build that into a kind of smoothing technique where I start off with, I sort of like in the good Turing idea, I sort of pretend that an event that I actually saw occurs a little bit less than it did, so I discount off its event count. But then I also add a component to the model which scores a word very highly in a context if it has a high continuation probability, that is, it occurs in a lot of contexts overall. And you can make this fancy and do it recursively all the way down, and this is what's known as Knaser-Nye smoothing, and this is actually the best known technique for n-gram models that doesn't involve some kind of deep learning. So, how do we know what models work well and what models don't? We have to evaluate language models, and this slide focuses on, it's a brief introduction to how this is done in the natural language processing literature. And it's going to connect to a basic idea in information theory that we covered recently. Let's view held out corpus data. So I trained a model, and I have new data that it didn't see during train time. I'll call that data D. It's held out data. I'm going to view that in a probability way as a sample from some distribution P over word sequences. Now my language model is another distribution over word sequences. It's not the actual corpus distribution for sure, because we don't have access to the corpus distribution. But it's an estimate of something like that, and we'll call that other distribution Q. That also puts probability distributions over word sequences. Now, it turns out that if I calculate the average surprisal, word by word, of the words in D under the model Q, that is an estimate of the cross entropy of Q relative to P. To spell that out, to review, this is the definition of cross entropy. I'm using slightly different notation here. So W sub less than I is the words preceding word I. So if I imagine sort of an infinite stream of text, and I'm always predicting what the next word is given the preceding words, there's some underlying probability distribution over what word will occur next. That's this thing. And then I use that to determine a weighted average surprisal under the distribution that I actually have at hand, Q. This is the cross entropy. I, of course, don't have P, so I have to estimate the cross entropy. And I can do that by taking into account the fact that by hypothesis, the data D come from the distribution P. So if I take a sample, then I can construct the empirical mean surprisal under the model Q from the data set D. So I take the average over all of the events in D, so it's going to be, the weights are going to be uniform over the number of words in D, that's the size of D here. And then I'm going to ask for each event, what is its surprisal? What is its conditional probability, the log of its inverse conditional probability, given the preceding words. So this is an estimate of the cross entropy. And this is very closely related to the standard performance metric that you'll see in the language modeling literature, which is called perplexity. In particular, if you exponentiate this value, you get out this thing which is the perplexity, which is the geometric mean of the inverse probability of the data given your model. And I really strongly suggest that you prove to yourself that if I exponentiate this thing right here, the estimated cross entropy, then I get out the perplexity. It's actually a very simple thing to do, but it's a good thing to do just to confirm your own confidence in your mastery of this work. Okay, I do want to call out that there are some ideas that are very natural that we haven't implemented yet doing any of the n-gram things that we talked about. One is that naturally you want to generalize across contexts or events that are, so some contexts like, for example, the soup that and the broth that are more similar than the soup that and the idea that. N-gram models, as I've described them to you now, have no way of capturing that similarity structure. So they don't generalize across similar contexts. Likewise, they don't generalize across similar events. So n-gram models don't take advantage of the fact that if the word soup is likely in one context, it's some evidence that maybe broth is too. Another thing that the n-gram models haven't done, as I've described them so far, is varying the window of the context, representing proximity to the event in nonlinear terms. All of these things are things that these models don't do so far, but contemporary deep learning techniques, which we'll cover later on, automatically do. Of these models that don't use deep learning techniques, of the non-neural language models, the best of them is Knaser-Nye smoothing, which I briefly described to you. You can study the details in any of a number of references. This is a classic paper, Chun and Goodman, 1998, and this is a classic graph of them showing that over a bunch of training set sizes. They took a bunch of competitive models, variants that incorporate a number of the ideas that we talked about. A particular version of Kneser-Nye modeling that they developed does better consistently than all of them. So if you're looking for the most competitive non-neural language model for a particular task, which you often might want to do as a baseline, then use modified Kneser-Nye. Nevertheless, deep learning trounces the best n-gram language models. So this is a paper from 2016. This is the n-gram, the best n-gram model that they had in this case. Its perplexity was 67.6, and this model came up with a neural language model that cut that perplexity in over 1/2. And actually, today we have models that are even substantially better than that. So deep learning trounces n-gram models, but nevertheless, these are extremely useful models conceptually still to build up your understanding of the challenges that are faced in sparse data estimation for language. And also, once again, they may turn out to capture features of human knowledge. I'm now in a position where I can go back to the 3 language models that I introduced to you anonymously, and I'm going to reveal to you their identities. So language model 1 actually is a Kneser-Nye smooth n-gram model. And you can see that its surprisals are just much higher in all cases than the competitor models. The second one is a long short-term memory model. That's our neural architecture that we'll cover later on in the semester with 80 million words of training data. And the last one is the very famous GPT-2 transformer model, which has an estimated something like 8 billion words of training data, which is many human lifetimes worth of training data. And you can see that they all have interesting performance, and the neural language models are much better in terms of these are all legitimate sentences, and the neural language models much lower surprisal on these sentences than the n-gram model. So neural language models are still, they're still the ones that you want to go to if you're looking for a high performance model. But I want to end with a scientific insight that we can gain from looking at n-gram models, and in particular bigram models. So I want to go back to this notion of collocationality. Here's one more example. Large majority, vast majority. They probably mean something like the same thing. But I think you probably all have the experience that vast majority is obviously the way to say the meaning. Vast majority is a collocation, large majority is not. And the tools that we have in place now actually allow us to put forward a hypothesis about how to formalize this notion of collocationality using the tools of probability theory. Intuitively, if 2 words go together, then if you condition on one of them, then the other one should have high probability. So if I do a left to right model, then I would say that given the first model, the probability, the first word, the probability of the second word should be high. And that should be a measure of collocationality. So that should be hold when the words are collocational. There is a shortcoming to this initial formalization, which is that all else being equal, a high frequency word will be more probable than a low frequency word. So for example, the word the is high frequency in a lot of different contexts. But generally, I think we feel like the is not a very collocational word at all. It doesn't have many collocations at all. We can factor this out by just dividing out the probability of the event word, w sub I. So this is the conditional probability of w sub I given wi minus 1 divided by the unigram probability of w sub I. So this factors out above and beyond a word being high frequency, how likely is it to occur in the context of wi minus 1. Now it turns out that if you stare at this a little bit more, you'll realize that this is very closely related to something we covered in intro information theory, which is the pointwise mutual information. Remember that P of wi given wi minus 1 is just the joint of Pi and I minus 1 divided by P of wi minus 1. That's this thing right here. So this is actually right here, this piece is this thing right here. And then once we divide, it's just this thing right here, just to clarify. It's that. And so if we divide now by P of wi, we get this whole thing right here. And if we take the log, that gives us what's known as the pointwise mutual information. So the hypothesis is that the pointwise mutual information, which formally is a measure of how much more commonly these 2 words could occur than they would if they were conditionally independent given everything else, that the pointwise mutual information actually captures collocationality. And so I'll let you evaluate this hypothesis yourself. What I've done is for all of the collocation, non-collocation pairs, I've gone to the Google Books Ngrams dataset, and I've computed using relative frequency estimation the pointwise mutual information of each of the bigrams at stake. Young childhood, early childhood, mass destruction, illegal destruction, good cuisine, ethnic cuisine, and large majority, vast majority. And you'll see that in all of these cases, they all have positive pointwise mutual information. They co-occur more often together than you would predict if you were to just draw two words randomly out of a hat. Now that's probably something that can be explained by syntax. These are all adjective-noun pairs, and adjectives and nouns can occur next to each other. In fact, that's a canonical way to use adjectives. And so if you draw two words at random separately, they're relatively unlikely to be an adjective and a noun compared to the bigram probabilities. So the bigram probabilities are all above what they would be by chance under a unigram model. However, some of these bigrams have much higher PMI than others. And I'll leave it to you to judge whether it's always the case that the word that has the higher PMI in the pair is the one that feels more collocational. For me, it does. So, to summarize everything we've covered today, language models are probabilities over word string. These are a fundamental key component of both scientifically studying human language processing and also natural language technology. They naturally serve as a prior for Bayesian word string identification accounts, for example, speech perception, and we've seen that they can explain interpretation biases. They are simple and interpretable language models. We saw that interpretability when we were looking at bigrams and collocations. They're not great models of human linguistic ability. They definitely badly fail to capture some core things that occur in human language. They're also not competitive in a technological setting these days compared to modern deep learning. We saw a lot of the weaknesses of maximum likelihood estimation, but we were able to bootstrap maybe some of our intuitions about some of the challenges in probability estimation that occur for human language. And finally, in the last example, I hope to at least have made something of a case that perhaps some patterns that we see in n-grams do capture features of linguistic knowledge, like the sort of intuitive sense of collocationality that words go together. Thanks very much, and looking forward to talking to you in class.